All right. Thank you so much for having me. Thank you, robots, for helping set this all up.
Thanks for that.
Love it. Why don't you just start off by telling us where we are, what all these robots are doing, and what you guys are up to?
My name is Jang, and I work at 1X Technologies. We are a humanoid robot company based out of both the Bay Area as well as Norway, where the company was founded. And the mission of the company is to make safe humanoid robots for solving the world's labor challenges, as well as providing creature comforts to the home in terms of like chores and things like that.
And so the intent is to have one of these like in my house.
That's the idea.
Yes, that's awesome. I think there's many humanoid robot companies that people have probably heard of, or at least there's like more robotics activity than there was definitely 10 years ago or 20 years ago. You know, it's actually feasible now that we could imagine something like this in at least a warehouse, if not an actual like a house, like someone's home. Why is that? Like, what has changed recently that has allowed us to get to something that is like this?
Yeah, there's a few trends that have basically made general purpose robots like you see in cartoons, or Susie the robot, that vision much more possible and plausible to many entrepreneurs these days. One is in software, one is in hardware, and also the broad sort of trend in labor demands and demographics. So it's a mix of, I guess, software technology, hardware technology, and just demand.
Yeah. And I'm sure we'll dive into those very deeply, like the different aspects of it. Definitely the hardware and the software sides. First of all, there are lots of these companies that are like attempting the humanoid form factor. And we'll get into that as well, like why humanoid versus just specialized robots to do specialized things. But maybe to begin, like, what is it about your approach here that maybe is different than the other folks, but also like what's the same? Like, what are those things that are common to all these robotics companies that make them possible?
So there's a long history of humanoid robots, starting from, early pioneers like Honda, Asimo, and all the way to, 1X, which started in 2015, and to new entrants in the space like Figure and Tesla, and a large number of Chinese humanoid robot companies that started after, let's say, the Optimus project was announced. But the thing that sets 1X apart is that we are vertically integrated from a hardware perspective. So we do all the motor manufacturing ourselves, and in fact, cool. the foundation of the company was actually in motor design, basically making a very high torque to weight motor. So that's one way in which we're differentiated. I can go into why sort of owning that hardware vertical integration is important. The way we're differentiated in software is that our AI strategy is very, let's say, like ML focused, and kind of is taking on the learning first principles that we see in like ChatGPT and LLM based technologies to robotics in a very rethink from ground up way. And finally, I think in our go-to-market strategy, because of the way we're designing our hardware and software, it allows us to tackle the consumer application much sooner than what people would think. So a lot of the humanoid players in the space are trying to ship to applications like factories and settings where the robots are cordoned off from humans. But in our case, we think that robots like this will be safe enough to interact very close to people, as you see here.
Totally. And that's like probably the core thing is safety, and just making sure that the robot isn't going to go rogue or whatever. Like so maybe for an industrial robot, you want to be super strong. You want it to be like, like faster. I don't know. But for this, there's different constraints. Like you don't actually need this thing to be super speedy or super strong or whatever. You just need it to be safe and smart and able to do things that you ask it to do.
Let me add a small correction there. So it's a common misconception that like safety is actually just sort of inversely proportional to strength or something, right?
Sure.
So maybe like your common guess would be like, okay, a hydraulic press is something you would have in a factory and you don't want in your home.
Right.
It turns out that strength is not the only factor in safety. For example, a human is very strong. I could arm wrestle you, exert a lot of torque on your arm. But it's also not going to break your arm unless I apply excessive torque, right? But a human can apply a lot of force and lift very heavy things. You could have a system that is weaker than a human arm, but still actually unsafe from a energy perspective.
Okay, do you want to swap out our implement here? See if we can. Okay.
Could you get us a whiteboard?
This is awesome. Bye. Thank you for holding our microphones. Oh, that's hysterical. I love it so much. Thank you. Hysterical.
All right. So
you want me to hold it here?
Sure. Yeah. There's a bunch of components that go into a robot that matter a lot from a safety perspective. So to simplify things, I'm actually only going to show you one motor
Mhm.
in a robot, which I'll depict as this circle. And, normally this is in a leg or an arm or something, but actually to make it even simpler, I'm going to use an analogy that makes sense from sort of a layperson perspective that is maybe not that familiar with robots.
Okay.
So imagine you have the motor that's rolling on the ground, right?
Sure.
A wheel.
Yeah.
It's her first invention, right? And around the motor, you have a box that's like a cardboard box that covers the wheel. So you've got like, it's a little cart. And this little cart is driven by the motor and it runs into a person.
Uh-oh.
Collides with a person. So, and let's suppose the person is kind of, in your Bond villains.
Yeah. Just smashed against the wall. Yeah. Okay.
The tide, right?
Yeah. Okay.
So how bad is this? Well, let's say the motor is really small, right? It's like a small toy, like a RC car or something.
Yeah.
And it's a big box, but it's a small car.
Sure.
So it's a tiny little motor here. It's probably not going to hurt. The box will gently push into someone, and let's say it's going at some speed. I don't know, like 3 feet a second or something.
Yeah.
Or for 1 meter per second for the metric units. And
I get in trouble for not using metric every once in a while on this channel.
So that's not too bad. Like if it's a small car. And now imagine inside of the box, you have a much, much bigger car, like the size of a truck or something.
Yeah.
Well, this is a problem now.
Right.
This will smush the person. And so from the outside, you could imagine the box is moving at the same speed, but it really matters how big the thing inside is, right?
Yeah, totally.
So what is at play here is basically the mass.
Yeah. Mass times acceleration is force.
Force.
Yeah.
So by conservation of energy, basically the total amount of energy in this system when it collides with the person here is going to be like you're compressing a spring, your sort of high school spring, okay,
Totally.
that is moving by some distance, and you want to make sure you're not compressing the person too much, or at all, really.
Yeah.
So the kinetic energy transferred onto the human is 1/2 mv squared, and that's this system, right? So your mass of your system is here.
Sure.
So this is very intuitively obvious. Big car, you don't want it to run with someone. Small car is safe.
Yeah.
But what is much less obvious is that actually the kinetic energy is very dependent on the velocity of the system.
Sure.
So if, let's say, instead of 3 feet per second, this was actually 6 feet per second,
Yeah.
then your energy goes from 1/2 m, like 9 to 1/2 m.
36.
36, right?
Yeah.
So this is a much larger amount of kinetic energy.
Yeah.
So the point of safety is that not only is heaviness a factor, but also speed. So that's kind of step one.
Sure.
Which is pretty intuitively obvious, right? So now let's imagine you have a slightly modified car,
Right.
where you have a wheel of the same size, like as this one here, and you have another wheel that is spinning very fast and driving this one.
Yeah.
So in robotics, we often have actuators with gears in them. And
Yep.
so imagine you have, a wheel here and a wheel here.
Yep.
And this is like M1, M2. And this wheel is spinning at, the same speed as this one. So, and this one is the one touching the ground. So this thing is going at 3 feet per second. Same as before.
Yeah.
And let's imagine distributing the mass of m between these two here.
Sure.
So, the total, if you weigh this thing, if you just put this whole thing on a scale, you'll find that the masses are the same. So is it the same amount of safety when you have this system, colliding with a person here?
Sure.
Well, it turns out the answer is no, because if this one is spinning, if this is a geared system and this one is spinning
Really fast.
what n times for every one revolution of this one,
Sure.
then you end up having a system where the kinetic energy of this wheel is 1/2 m1 k times v squared. And the kinetic energy of this one is 1/2 m2 times v squared, or k squared v squared.
You're missing a K in that one. Is that right?
So this is this wheel here.
Oh, okay.
So
Got it.
it does not have the
It doesn't have the gear. Yeah. Got it.
right. So it's basically this term here, and what you'll notice is that it's like very similar equation to before, except the kinetic energy of the smaller wheel here or sorry, not the small, the wheel that's turning faster is actually going up with a square of k.
Yeah.
So if this one is turning, let's say, 100 times for every one revolution of this, which is actually some of the case in some actuators that we find on the market today, you end up with a 10,000 factor in the kinetic energy from the rotation.
Interesting.
Of this.
So intuitively, that actually doesn't make sense to me, because I like, why wouldn't we just treat this as a black box and it doesn't matter what's happening inside? It
Right.
just matters like how fast it's going.
You see the cardboard box moving at some speed,
Right.
and it collides with a person.
Sure.
So I guess if you don't know what's in the box, then it's pretty clear that like if it's a heavy object in the box
Yeah.
and it's driving the box, then all the energy will be dissipated to the person. So that's
Sure.
what's very unintuitive.
Oh, there's more kinetic energy that's trapped in those wheels that are moving it.
Even
Oh,
if you
wow.
weigh the two systems, and let's say M1 plus M2 is the same as this mass. So
Interesting.
If you put them on a scale, they're the same mass.
Yeah.
But when they're running and operating,
Because it's because the wheels have to stop turning, and so so you're basically imparting the energy that like you're getting run over by the wheels that are spinning inside. Oh,
in
fascinating.
order, like, you know, this, assuming there's this wall here, this has to come to rest upon
Right. Right.
coming into contact with the spring here.
Yeah.
So the amount of compression of the spring is basically the amount of work performed by the kinetic
Totally.
energy stored in the system.
Yeah.
Assuming it comes to rest.
And if things are spinning really fast, then that is kinetic energy that also has to be dissipated.
Some robotic
Fascinating. Okay.
actuators, like for example, those designed by KUKA and so forth, have very sensitive sensors that make sure that they can disengage this fast
Yeah, exactly.
internally
Yes.
once they come into contact. Right?
Because then it doesn't matter. The kinetic energy is dissipated like by itself, not into
So you can
the
imagine, like,
target.
if you have a special sensor here, which is like I have this very fast sensor that
Yeah.
compressing this even a little bit too much and too fast,
Yeah.
I will just disengage this motor from this one.
Totally. Yeah. Right.
And that's like a safety mechanism that's been implemented in, let's say, actuators like KUKA.
Sure.
To my knowledge, I'm not an expert on this one. But that's what I understand to be the case. So yeah, the very like counterintuitive thing about robotic actuators is that it's not just about weight; it's about the flywheel that's spinning inside of your robot
Interesting.
that must come to rest when it collides with an immovable object. So like, how does this relate to a robot? Well, so yeah, this is like a car, but imagine instead that you have like a leg,
Yeah.
and it's now like kicking a person.
Yeah.
In the same way, like if you have a geared mechanism that is spinning very fast and then slowed down by a gear reduction, when that thing is then coming into contact with some sort of immovable object, that will result in a large amount of force being dissipated to whatever the end of this is.
Okay. Got it. Okay. You want to take this down and then, okay, perfect. So basically what that means to me then is the factor of safety is like, it's like a gear ratio thing almost like you want to have it so that you don't have to spin your internal motors very fast in order to exercise the same amount of force, whatever you're trying to do, like closing a hand or moving a leg or that kind of thing.
And so if we look at humans and like small animals, we're quite safe in the home, and like, you know, I can like pat you on the shoulder, like hit you pretty fast, and it won't grievously injure you, right?
Yeah.
And that's because we don't have spinning parts inside of our bodies. We have these very slow muscles that contract very, very slowly, as opposed to like a dynamo that's spinning at 5,000 RPM.
Sure. Wow, fascinating. So most robotic companies, or like most other robots, do have the very fast small motor that turns the larger thing that eventually actuates into the thing you want. But you have all designed a way that you can basically have is it larger, is it slower turning, or both, and then that just is distributed out to where it needs to go to affect things?
Yeah. So I guess in the sort of motor catalog, they're known as high torque, low speed motors.
High torque, low speed motors. Awesome. And you guys built those?
Yes.
That's awesome.
The company started from building motors. This was before my time, before I joined 1X, but the company was founded on like basically this principle where the CEO Bernd, he kind of worked out that in order to make a safe humanoid for the home, if you work backwards from the requirements of physically what must be true about the actuation system, you need to have motors that are higher torque and lower speed. And that required redesigning motors from scratch. It's almost like the same process that Tesla went through with designing their motors, but almost like sort of an inverted set of requirements.
Sure.
So Tesla, to make a motor for a car, you want high speed, low torque. For making a safe humanoid robot, you want high torque, low speed.
Does that also mean then that you can afford to have less like crazy sensors? Like you don't need that little kill switch thing to be on your robot as well?
Correct. Yeah. So
Okay, interesting.
the active like torque sensing that you would put at the edge of your, your end effector, like the wrist or something of a KUKA arm, we can instead basically get that passively by just having the actuation system be known as what is backdrivable.
Okay.
So back
Sure.
drivability happens is that when you have very low gear ratios, you can impart forces on the end effector of your or the lever arm of your system and basically drive the gear in reverse. If you have a high gear ratio, it becomes what is known as stiff, which
Yeah.
means that you can push very hard on it, but it doesn't budge. And that's unsafe because it's sort of like the
Yeah.
equivalent
I mean,
of a semi-truck.
it'd be like if it grabbed your hand to give you a handshake, it couldn't let go as easily. So and if it wasn't back drivable, but if it is back drivable, then you can kind of like pull its hands open, basically.
That's right. So an example actually in the case of hands is if your hands are not back drivable and I asked it to close on an object,
Yeah.
it won't care if there's an object in there or not. It'll close the hand.
And it just wouldn't stop. It like
Yeah, it wouldn't stop. It would
Okay.
just like squish whatever's inside. Right?
Mm.
So like to do a lot of useful tasks or to like work alongside people, you want to really make sure that you're not squeezing way too hard
Sure.
the person.
And is that so? When you are telling a robot grab a grape or something like something that's very fragile and could be easily broken, do you tell it like? And maybe this isn't true for all robots or something, but I'm curious. Like, do you say? Does the computer of the robot say impart this much force, or does it say move this much, or does it say spin this fast? Like, what is actually like being told to the end effector?
Yeah, that's a great question. So it is possible to use a variety of robot arms to actually pick up a grape and show you a video of a successful grape picking up task. What becomes really important from a hardware perspective is what happens if the predictions are not accurate. Like if you have a perfect trajectory replay of picking up a grape, you can use almost any robotic system to do this.
Sure.
But if let's say there's a small inaccuracy in estimating where the grape begins and where it ends, a very stiff system, one that is, let's say, not back drivable, will crush the grape. And a more compliant system will apply some amount of force, and we can limit the amount of force it's applying, and that won't squish the grape.
Okay. But it's so, but still, like the command that is being sent to the thing is move this much, or is it go until you feel resistance and stop?
Yep.
Or
if you have a stiff robotic system where you have high gear ratios, the only way you can control it is to say move this much.
Okay.
You don't really have a choice to say I want this much force because you don't get the feedback from the system.
Okay, got it.
If you have a compliant system, you can control how much force you want, but also if you have a good enough joint encoder, you could tell how much do I want to move.
Okay, awesome, very cool. So what are the other sort of like major departures that you can have on the hardware side? So we're still talking like hardware, and we're talking about the the components that make up an arm and a torso and legs and like the eyes, I suppose, things like that. Like, is your robot very differentiated in terms of its like optics, or in terms of its like larger like larger like limbs, I guess? Like, I don't know what you would call it. Like, what are the other ways in which it's different?
There's a quote by Alan Kay, which is that people who are serious about software make their own hardware. And he said this in the context of the personal computing revolution. But what he, I think, meant by that is that when you're trying to build a new type of technological paradigm, whether it's the personal computer or the iPhone or social media, you really need to think through everything from the software, the UX, all the way to the distribution channels and how you bake software decisions into hardware. So like thinking through everything is what really serious software people do.
Mm-hmm.
A lot of our hardware decisions are actually informed by how we plan to do AI, as well as how we plan to do our go-to-market, and also the UX as well. I can't go into too many details on like, all the sort of secrets we do into our actuation technology, but I can say that there's a reason why there's no off-the-shelf humanoid that you could just deploy in anyone's home today, is that it comes down to a lot of really careful design choices around what the kind of software you plan to run on the robot is. Like, for example, how much compute do you want on it? That is sort of informed by what AI strategy you're using. And if you take one approach or another, you might actually end up with very significant compute constraints. And that in turn influences how you design power. And that in turn it just informs how much space you have on the system for power versus the motors,
Sure.
and where you put the motors, and so on and so forth. So all these decisions propagate.
Interesting. Yeah, I mean, like a robot is a super integrated system with a lot of trade-offs in the same way that a satellite is. Like for ours, like, I mean, some of the biggest constraints for us are things like thermal. Like, you have to make sure that you're dissipating all the heat. Like, we don't get the benefit of convection, so we just have to like dissipate through radiating off of the panels. We care a lot about like the size, form factors. We've got to fit it on a rocket. Like there are a lot of like driving constraints that lead us to make different decisions. What are sort of like the hardest trade-offs that make you make the hardest decisions in terms of the hardware of this thing?
So a big one is safety. As I said before, like kinetic energy is sort of a function of your mass and your velocity squared. So we want to make sure that the total internal velocity of any given component is not too high, and also the mass of the whole system is not too high.
Yeah.
For example, if it runs into you at full speed, we want to make sure that it's not lethal.
Mhm.
That is a very dominating design factor in kind of how we choose to like include something or not, and it really biases us towards simplifying the system. So like removing pieces that we think we can simplify, reducing weight is a big constraint for us, and another difficult design component is building very dexterous hands. So because we want to build a general purpose home robot, we want to be able to do a lot of different tasks. And we've have a lot of experience working on our wheeled bimanual manipulator Eve. It can do a lot of tasks, but it definitely cannot do all the tasks. And so from our experience working with parallel jaw grippers with a lot of dexterity, we want to kind of go to the next level and do hands.
Did you say parallel drive gripper?
Sorry, parallel jaw gripper.
Jaw grip. Oh yeah, so just just claws.
Yeah, the claws. Yes.
Cool.
When you're building a dexterous hand, there's so many degrees of freedom in the hand, and essentially what you're building is not just the head, but actually the forearm.
Yeah.
Since all the actuation of the head in a human actually comes from the forearm, not the hand itself. Right. Like so, once you build the forearm, that has a lot of implications for how you build the upper arm. Once you build the upper arm, that kind of propagates to the rest of the body.
Sure.
So a lot of our design decisions in Neo are actually like motivated by solving these kind of very difficult miniaturization problems that we have to do with the leg and the limbs, and it ends up that like that kind of requires designing the whole system end to end. You can't just build an arm by itself and sell that as a standalone product. It really has to be integrated with the whole system.
Got it. So you are like the way that the so first of all, we should establish like this is version 1, the one that was holding our microphones earlier, and version 2 is a bipedal walking with hands like humanoid.
That's right.
So I now that you said the weight thing, I think that like makes a lot of sense to me why you would want to swap out the tires for legs. Like, I mean, this presumably is a lot of the weight. Like the base of that thing is a lot of the weight because you don't want it to tip over, and it has to like the wheels are big and the base is big, and that's probably where a lot of like the power electronic stuff goes. Like, I imagine that's extremely heavy compared to the rest of the system. So it makes sense that would be a reason. Is that correct? That would be a benefit of moving to bipedal over the wheeled thing?
Yeah. So I get this question a lot. Why go bipedal? The sort of quick answer, which is true, but requires a bit of unpacking, is that the world is made for humans, and therefore it makes sense if you want to work in that world to build a human-shaped robot. But a lot of roboticists say that, oh, you can make some compromises, right? You could swap out the legs with something like a wheeled base with one leg. You could maybe even go further and just have a pole with an arm on it and a sort of base, as there's a lot of robots that look like that. Or maybe you could have a different robot shape that maybe like a dog with an arm on it or something, right? So everyone acknowledges that humans are sufficient, but a lot of people are not sure if it's necessary. So let me explain why they're actually necessary, and why even something like Eve is not actually good enough for the full scope of generality in the home. The home has a lot of cases where you want to reach pretty far. Let's say reach across a dining room table to pick something up. Reach under a table to pick something up, wipe things on the floor, pick something up off a counter. In these spaces, it's very hard to come up with a robot form factor that can reach a long distance and pick up a fairly heavy object without either bracing itself on the countertop or moving its center of mass to be closer to the object you're picking up.
Oh, that's because can I guess? So it's basically like when I'm picking something up over a countertop, I fling my leg back to make sure that I, can balance. Like I have to have a counterweight that keeps my center of mass balanced, or I don't fall forward or fall back while I'm doing the reaching.
Let's suppose your back is against a wall and you're leaning forward.
Yeah.
How would you pick up the object without being able to fling your leg back? A human could still do it, right?
If you just are leaning far.
Yeah. So how would you pick up an object that's far across the table?
I'm trying to think
but your back is against a wall.
I don't know. I think you have to have some counterbalance to make you not fall. So
you can put your hand on the table.
Oh, sure. You can brace yourself.
You can brace yourself.
But you could do that with this too. That's what I'm trying to figure out, because you could do that with that guy.
That's correct. So you could brace yourself and lean over.
Right.
That does require your torso to be able to lean over.
Sure.
And so yes, then you need like a lot of
hinge at the waist. Yeah.
Mobility there. You can come up with a lot of different scenarios where that particular solution would not work.
Sure.
So maybe like in another scenario, you try to pick something under the table.
Yeah.
At which point your sort of pedestal that your bimanual manipulator is mounted on might not be able to go low enough or something.
Yeah.
Right. And you can sort of come up with like a dozen or so very common household scenarios, like where you want to pick up something that's at a distance and you need to get around some obstacle.
Yeah.
The human form is very ideal because it's very easily configurable. So you can have a wide stance, which basically gives you a very wide support region with which you can, move around and not fall over.
Yeah.
But if needed, you can also shrink your footprint so that you can step over a very crowded, like, living room full of children's toys or something. And even if that's some exotic scenario, you can even use your other libs to brace yourself, like in the game Twister or something.
Sure.
Which is an extreme example of this.
Yeah.
But basically, I strongly believe that the home environment is much more like a game of Twister than it is like your typical, drive around on a floating kind of a base and just pick up things like this.
Interesting. So it's like you can change the base size. You can change the center of balance or the center of mass or whatever. You can
change your contact points with all 4 of your libs. Climbers actually use more than 4 limbs. They can even use their elbows, knees, and so forth.
Fascinating. Okay, yeah. Like, what's the difference between that and a climber who has his legs tied together? It's like, that makes sense.
Yeah.
Fascinating. Cool. Yeah, I've definitely heard people say like, the world is designed for humans, and it always struck me as kind of just like BS.
It's a bit of a knee-jerk answer. If you take any standard bookshelf, you'll notice the bottom of the bookshelf has a little inset into the bookshelf.
Sure.
Do you know what that's for?
Cords? I don't know.
It's for your toes to go into the bookshelf.
Oh, underneath. Oh, I know what you're talking about. Oh, cool.
Yeah.
Nice.
It's because it's very hard to reach into a bookshelf if you have to stand at, let's say, 3 or 4 inches away from the bookshelf.
Huh. Fascinating.
Because you're actually tipping yourself over a little bit too much when you do that. So by having toes and having that little inset area into the bookshelf, it's much more comfortable to pick up books and whatever out of a bookshelf.
Interesting.
And so homes are, and this is the case in cabinets and kitchens. There's always this little inset that you can stick your feet under the counter for.
Yeah, totally.
So you could have a much larger reach.
Wow, fascinating.
If you compromise on that and you make a robot base that is not feet, let's say a big blocky box with mass, you're now 6 inches farther away from where you want to reach than you should be. And now you have to add extra mass to your base so that you can cantilever yourself against the reach. Most robot companies, like for example, I worked at Everyday Robots where we had a large base like that. You end up making the compromise where you just have a shorter reach distance.
Okay.
And, that results in fewer tasks you could do.
Interesting. Okay, taking a step back to the hardware side, like kind of as a whole, I'm curious, like, so are there certain things that all robotics companies are just doing now? Like we never really got to the like what made this possible just now thing. And I think that my guess is that some of the answers must be there are components that just sort of everybody uses. Like everybody has the same sensors or like a visual thing, or like everybody uses the same materials that like didn't exist before that are just lightweight or something. Are there things like that have like kind of helped the whole industry go forward that are also helping you guys?
Sure. Cost of actuation technology has gotten cheaper. So even though many humanoid robot companies are not making their own motors, it's become very viable to make your own humanoid robot from off-the-shelf parts. I don't think they'll be as safe as ours, given that the way we've designed our motors, but they'll be reasonable for some set of applications. And that's why you see a lot of humanoid robot companies that are quickly springing up, going into maybe factory settings, right? Because they work now. And what used to cost, let's say, hundreds of thousands of dollars for one arm is now very feasible to make your own humanoid robot with that cost. So it's like for X dollars you could buy one arm, and now you can buy a whole robot with that cost. So that's the hardware side of things.
Yeah, and I'm sure there's an answer on the software side. So maybe this is a good transition to that. Like let's so tell me just at a broad overall level, like what is your approach and how is it different than other people's approaches to AI for robots?
So traditionally in robots for the last 5 or 6 decades, the predominant approach is to think about robotics as a pipeline where you go from perception, you go from camera images and sensors to a very compact understanding of the world, and this is known as perception. Then you plan some sort of high-level task, like how do I make some recipe in my kitchen, by breaking it down to logical sub-steps. And for each of these logical steps, like pick this up, put it down, open this jar, you have a motor primitive that can execute that skill. So it's this very classical software engineering paradigm of breaking down a very complex problem into composable parts that you can put together pretty easily. That is still a very predominant paradigm of robotics today in many commercial applications. But if you've been paying attention to progress in AI technology, in the last 1.5 decades or so, there's been this really massive revolution in how we build AI systems for chatbots and other kinds of AI like capabilities, like playing games and so forth. And that approach is to basically throw away all of our preconceptions about how the solution should work and just take a lot of data on what the agent or AI sees and predict what it should do. And so the software unlock for general purpose humanoid robots is that this type of technology where you could train a single neural network or AI model to do hundreds or thousands of tasks is now feasible. You see this with applications like ChatGPT. A humanoid robot makes a lot of sense from a hardware investment perspective if you can onboard hundreds or thousands or millions of tasks very quickly. If you're only making one task a year, a humanoid robot doesn't make as much sense because you're better off maybe just building a cheaper specialized application and building a new robot every year to do the next application, right? But if you're able to scale up to many tasks very, very quickly, then the higher cost of 4 limbs is much more easy to swallow than building just one limb for one customized application.
Interesting. So intuitively, like if we're comparing it to just a normal LLM, like obviously one of the things that made that very possible was this like insanely huge data set that is the internet. Like there is an immense amount of semantic data that you can pull from everybody writing sentences on Reddit and on whatever for all time. I don't think that there exists such a data set for you guys. Maybe that's wrong. But how do you solve, or how do you get around that? How do you get around not having this massive pool of data to train these things?
The word on the street is that the modern language model pre-training set is something around 15 trillion tokens. So then your question is really, do we have 15 trillion robotics tokens?
Yeah.
And what is a token?
Yeah.
And so that's a question that we're really interested in trying to find out. What is the sort of best way to count how much data we have? If you count a robotics token by, let's say, every image is representing a few tokens, and you try to reasonably compress your understanding of images to as few tokens as possible, then by our counts, with our current and planned deployment of NEOs, we'll have roughly that number of tokens within 2 years.
Really?
Yeah.
15 trillion within 2 years?
It's not.
Wow.
It's not hard to
Wow,
do.
interesting. Because you're treating a frame of a video
As some number of tokens.
Okay, got it.
So you could imagine, like, let's give it our best shot to compress every frame into some number of tokens.
Yeah.
And of course, there's redundancy between frames in a video, right?
Sure.
There's also like you need to count carefully how many tokens in a video there are. So assume you have some compression rate there as well.
Yeah.
And then also, like, if you have 2 different videos that look almost exactly the same, you can't double count those tokens as well.
Sure.
So
yeah.
in fact, like if you're deploying in a factory where it's doing exactly the same task over and over, you can't count like all those hours of the same
Totally.
tokens, right? You have to be pretty honest with like the diversity of tokens and make sure it's comparable to Reddit or something.
Sure.
Reddit also has redundancy, but
With
like,
memes.
with memes and so forth. But you got to make sure that like the way you count tokens has to be roughly comparable in, let's say, intelligence versus data set size to an LM data set.
Interesting. But I mean, and so it seems to me that that's not enough data though. Because I mean, you do get the data of here is what is happening in the world. And I guess you are affecting that. So it can sort of infer its actions, like its effect on what happened in the world. But it seems to me like you would also need to have all the telemetry from this thing of like, where is my arm and how hard am I gripping and all that stuff too.
So in addition to counting, let's say, every frame as some number of tokens, you also have to count every action you take and every, let's say, telemetry on the robot's pose as some number of tokens. And for each of those, you can go through the same exercise of trying to compress it into as few tokens as possible using the same techniques that LLMs have done with training tokenizers. And once you have done your best job at trying to compress it, then you can sort of sum it across your data set. And you want to make sure that your data set is relatively deduplicated. So with this estimate, and assuming you're deploying your data collection in very diverse settings where you don't have a lot of duplication, you can get to 15 trillion tokens with some concerted effort.
Wow.
And the reason why this works is because they're collecting data a lot of the time, right? So you could actually have them actively go out and try to find tokens that are interesting to them as opposed to just the sort of same picking task over and over and over again.
Sure. Cool. That's interesting. And is a piece of it too, when I heard that you guys started with this model before you went on to the full humanoid or the bipedal humanoid, I figured that this was a great source of data because I mean you have all of these robots and they're all just like doing since I've been in the office they've been just like doing things, grabbing whiteboards, holding like those are new tokens. Like you probably didn't have to hold podcast microphones before.
Yes, yeah. That's
so
the
like-
first time we had to do that.
Totally. And so that is training data. Like that is stuff that you guys can use to train that other one, right?
Yeah. So every time something interesting happens on the robots, we have it merge into our pre-training
Cool.
system, and our AI stack is very much mirroring how like a modern LLM company works with pre-training, post-training, fine-tuning, that kind of stuff.
Very cool. And what's the where in that process, or like what is the importance of the teleoperation for it?
Teleoperation, we view teleoperation as very important for our software in several ways. The obvious one is that it gives us data to make good models, and teleoperators can
Sure.
gather good data to train good models. And it shortcuts a lot of tricky problems around how you would autonomously gather that level of quality data via reinforcement learning or maybe a sort of handwritten controller or something. There's another one that's really important, which is how well we can teleop the hardware informs us a lot on what is the upper bound on capability we could expect
Because
to get.
humans rock, and if we can't do well teleoperating the thing, then the software isn't going to get that good either. Is that basically what it is?
It doesn't mean that the software cannot do it.
Sure.
But it certainly means that like if the human's not able to do it with the technology we have today, it's probably unlikely that we can do better than that.
Okay, cool.
There's definitely some edge cases. Like for example, superhuman Go playing is possible because they have a scheme that is not reliant on human data.
Sure.
You could also train robots to be very good at catching objects with one of those I don't know what those
Spatula?
ball and cup
Oh yeah,
games
cool.
are.
Yeah, sure.
Like you could actually get superhuman at this as well.
Interesting.
Those are kind of exceptions where you could imagine to do better than a human. But if you're trying to tackle the general set of all
Yeah.
skills that people can do, the best strategy we have right now is to imitate something like what ChatGPT does, which is gather data on a large set of tasks, train a big model that can do all those tasks. And for that, we expect that the sort of currently the upper bound of performance is human level.
So I would imagine there's like sort of two ways that you could like fine tune or like post train one of these models. One way would be, let's just reinforce it for doing good jobs and things no matter how it gets done. Another way would be, let's define like a ton of primitives or like a ton of like kind of common gestures and get it really good at doing those things. Like it's really good at grasping, it's really good at twisting, that sort of thing. Like, do you feel like you're more towards the unstructured or more towards the structured side?
My philosophy on how to tackle these very open-ended robotics questions is I'm just going to look at whatever generative model companies are doing today and think that that is going to be what robotics companies are doing 3 to 5 years from now.
Cool.
It's a trend that I strongly believe in because I've seen it for the last 10 years. So when I'm asked that question, I think like, okay, how does like OpenAI tackle this particular question, right? And the closest analog I can think about is like their agents and LLMs have access to tools. And for some tasks, they'll call tools, and for other tasks, they won't. Right. So I see this as a very similar choice. It's like, how much of capability do you want to relegate to specific tools that are optimized for tasks, and how much do you want to sort of have baked into one big neural net that does everything? In practice, right now, our system relies a lot on tool use, where we have a fairly small LLM that's calling these individual skills that are trained each by themselves, like one that is for opening doors, one is for picking up objects, one is for returning to a safe pose while not bumping into anything. So these the tools themselves are general; they're not like overfit to any particular situation, but they're like skills that can be called by, let's say, a VLM or something. We think that the field could evolve more so that you have a much more general model that does more things in the future. But in the sort of short term, casting it into a mostly LLM type problem where it's just LLM and some tools gives us the most capability in a short time horizon, right? But we're definitely interested in like making tools more powerful and also making the thing that calls tools have much more capability without having to call tools.
Okay, interesting. Is there any equivalent to the LLM, or I mean maybe like like literally Scale AI or something? Like they used to use very general, just kind of like anybody to do labeling, but now they've gone to like lawyers and doctors and experts and stuff. Is there any sort of like expert reinforcement that comes with these things? Like, let's get a master craftsman to like to build something or whatever.
Yeah. One of the things I'm super proud about, and in fact, this is what sold me on joining the company, is how good the teleoperation system is. There is a mix of things that go into making a great teleoperation system. One is the hardware stuff I talked about, where you have to be able to bang on things pretty easily and be pretty safe about like not breaking stuff, but also just like minimizing latency of teleop. So we've kind of optimized the user interface of our teleoperation system to the point where a new user can just learn to do some tasks.
I
pretty
literally
quickly.
did it today.
Yes.
I put on the glasses and I could immediately tear a piece of paper and it was easy.
And that was like maybe 2 to 3 minutes, right, of
Yeah.
like interaction. So we do see this very fast skill progression ramp up. We have some examples that where we can like, go to the fridge, open the fridge, get some ice cream out. It's the wrong flavor. You put it back.
I
and,
heard
like,
that this is part of the in-office culture. That
That's right.
If you want a premium snack, which includes ice cream, then you have to use a robot to do it.
Yeah. It's one of the ways we kind of force us to really dog food and understand the product from like a teleoperation standpoint. And like, regardless of who you are in the company, you have to like use the product, right? And
I love
if we're going to sell it to people, it has to be used all the time. So, yeah, we want to dog food the product. But yeah, the teleoperation stack is really good. And what we find is that there's a very fast ramp up in capability that saturates around 50 hours, maybe I would say of practice across a diverse set of tasks. At that point, like you could do quite a lot of things, most chores, I would say.
Hmm.
And then after that, I feel like most of the bottleneck is like further improvements in latency and maybe even starting to think about sensing, like giving haptic feedback, let's say, to the user, or hardware on the edge. Like now we need to go from parallel jaw grippers to full fingered hands
Yeah.
or legs.
No, but you do. So with that teleoperation, do you get like expert input on a task? Is that is your source of expert input? Is a human doing the
Who's
thing?
trained for a good amount of time in VR.
Got it. Okay, interesting. How much of the AI, how much of the teleoperation transfers from Eve to Neo?
So there's transfer in several ways. There's transfer in the data, which is a question I get often is like how much of the data that the data moat we've built on Eves can be transferred to Neo.
Yeah.
There's a question of like knowledge transfer of like what have we learned on Eve that we can carry to Neo.
Sure.
And I guess there's also a transfer on like how much better does the teleop experience get? How much better of a teleop system is it? Going from there. So which one do you want me to go into first?
I'm curious, the obvious things that are different are like you didn't have fingers before and now you have fingers. So you have to find a way to teleop fingers. That sounds really hard. Just wear gloves or something, or like how does that actually happen?
We're exploring a few different methods at the moment. But, can't share too much.
Fair
more
enough.
on that.
Fair enough. So that's obviously different. The legs are obviously different.
Yeah.
You have to find a way to do that. So it seems like the things that are obviously transferring are arms, kind of normal grip manipulation, moving around the world because you had an ability to kind of like steer yourself before.
Yeah.
But like what pieces? Yeah. What isn't transferring from one to the next? Like what of the data say? Like what is
Sure.
useful and what is not useful?
So on the teleop experience, in our current experiments, we found that it's actually even more intuitive going from Eve to Neo. So Eve is already very intuitive, but because Neo is even more closely matched to human, people just get it. Like
Cool.
it just works, right?
Yeah.
And it's not a huge surprise there, right? The one challenge going from Eve to Neo though is figuring out how you actually control the legs, and I can get a little bit more into actually why that is difficult. On your data question, there's a lot of good academic research that has showed how you take a large corpus of data and you get it to work on another corpus of data. I think that's often a problem that people think is a much bigger problem than it actually is, because once you have, we have a good number of robots out there as humanoid companies go, but once you kind of get to the volumes of Neos that we're planning to produce, the amount of Neo data we'll make in one day will basically eclipse all of the Eve data we've gathered so far.
Really?
So it's almost like from an engineering perspective, not even worth using
Because there's
Eve
so many
data.
more degrees of freedom, basically, or why?
Because our fleet will be so much larger.
Oh, sure. Okay.
We're making hundreds to thousands of robots.
Cool.
Yeah.
But so what is that process of mapping then? You mentioned that like people think it's hard, but it's not actually. Like, is it you just have to like define the map and then all the old data can be used? And is that why it is easy, or what?
So when you're going from Eve to a Neo, there's a sort of obvious backward incompatible change, which is that the shape of the robot is now different, and your old data now needs to be ported to match whatever shape of your robot is.
Yeah.
And that's going to take some amount of engineering work. And through various mechanisms, it is possible to transfer some amount of information. It could be a lot of information or a little bit of information from the old data to the new data.
Mhm.
And you can think of it, there's a sort of currency exchange rate of like old data to new data with some ratio that is less than 1, right?
Sure.
To get to new data. Now, that's going to take a certain number of engineering hours to port that data. But if our production schedule of Neos, is
That-
that happened, then basically it's almost not worth the
don't
engineering
even bother because you're just going to get so much more data. That makes a lot of sense. I think it is fascinating. It's like kind of like the Rosetta Stone or something. It's like you have to define the match from one to the other, and like that would be a lot of effort to go and do that. So you just maybe you don't even need
It's
to.
not the hardest problem in the world, but it is a significant amount of effort to chase down all the different ways in which Eve data are diverse.
Yeah.
And then for each of those cases, make sure that we're covering them and mapping them correctly too.
Hmm.
So we have the Rosetta Stone, as you say, like the
Sure.
mapping information, but it's just like, okay, it's going to take a certain amount of engineering hours to port certain X thousand hours of data to Eve, to Neo. But the scaling of Neo data will be so rapid that
It doesn't matter.
it's not clear to us that data will matter.
Okay. Very cool. So I think that it sounds to me that a big part of the bet then is that you can build a lot of these things and get a lot of them deployed. I mean, that you talked about that how your go-to-market is different. Is that kind of the main thing, that you want to get just a ton of these out there doing a ton of tasks across the world?
Yes, get to 15 trillion tokens. You have general purpose hardware that can do many tasks, so you don't have very redundant tokens. And by going into the consumer setting, you get the diversity of tasks.
Cool.
There.
Very cool. Are there things that you have to specifically do to try to design for manufacturing then? Because I imagine like you could build a bunch, like I don't know how many total of these have you built? Do you know?
We built something, I guess
Order magnitude maybe?
order of magnitude around 50 robots. I'd
50.
say.
Okay,
Yeah.
cool. So, but you want to build hundreds, thousands of the next one. So I imagine there's a much bigger like design for manufacturability thing going
That's
on
right.
with this
Yeah, we
next.
took a lot of the lessons we learned from manufacturing and designing Eve, and we made further optimizations. So Neo will actually cost less than Eve.
Yeah, I mean, just even like looking at it from over there, the materials are different. Like, I haven't seen inside this thing, so I don't actually know what the inside of it looks like. But that looks like manufacturable.
Yes, it was designed for manufacturing.
Is there anything in particular that you would highlight as like a change that happened from one to the next?
So when I mean vertical integration, I mean actually all the way down to the manufacturing level. And again, this is work done by other great teams led at 1X. I can't take credit for this, but basically, even the machines that manufacture the copper coils that go into our motors are custom designed.
Wow.
And it's because in order to build the high torque, low speed motors, you have to make special machines that can then make the subcomponents of those motors.
Wow. Damn. Yeah. I mean, this is the lesson that people have been learning and have been, applying like much more vertically integration. This is like obviously pioneered by the Teslas and the SpaceXs and things, but we've learned that it works.
Vertical integration is one of those long-term plays where VCs don't get it because you're like building a copper coil winding machine, and what is the total addressable market of a copper coil winding machine? And they don't get it until you have like the best, cheapest humanoid, right?
Totally. Yeah. Or you just have to, not rely on somebody else's copper winding machine because you're the biggest you're the biggest like buyer of these now. And
but then
whatever.
they can't get funding because the VCs don't see the vision of a copper coil winding machine.
Exactly. Crazy. Wild. Cool. I feel really good about all this. Anything else you want to talk about?
What would you use a humanoid robot for?
Ooh, good question. What would I use a humanoid robot for? So I have a pet rabbit. Great pet, by the way. Shout out to rabbit and rabbit fans. Like, they're much easier than dogs. They're equally cute. They're just as fluffy, but they're like way less work. But even that, I guess I'm trying to outsource that work.
Okay. And do you want to like check in on your rabbit once in a while?
Sure, and like see her and stuff. That'd be cool. Yeah, sure.
Okay.
Yeah.
Cool.
I don't know how she would react to a scary. She's pretty like hostile. So we'll see. We'll see.
Maybe if you have it wear your clothes, like it'll smell like you. And
Have you invented the smell-o-vision? Have you brought that into the tech stack of like make it release the pheromones that smell like a human?
No, I was thinking you just take your old shirts and you just
okay. That probably
dress
solves
the
the problem.
robot
But
as
you can, if you invent smell-o-vision, then that can be a new feature. That'd be great. Yeah.
Yeah.
Hell yeah. Well, thank you so much for doing this. This is
Thank you,
really
Christian.
fun.
Appreciate it.
Awesome. Thank you, robots.